Good afternoon, everyone. This is Hemalatha, myself. I'm working in Marri Laxman Reddy Institute of Technology and Management. Now, we have started lasers chapter in the last class. Today's session also we continue with lasers, but some of the topics which are Einstein coefficients. So, let us discuss today about Einstein coefficients. Now, here, Einstein coefficients are nothing but relating the three quantum process, that is stimulated absorption, stimulated emission and spontaneous emission process, which we discussed in the last class. Now coming to this one, to explain about the Einstein coefficients, to derive the relation between those three quantum process, let us consider a two energy level system. Okay, we can take an energy level system, but the basic system is a two energy level system. So let us consider a two energy level system. Now let us name these energy levels as the lowest energy level is called as the ground energy level. Then the second energy level is called as the highest energy level, or you can also call it as the excited state also. Now let us assume that there are n1 number of atoms corresponding to energy E1 in the ground energy state and n2 number of atoms corresponding to energy E2 in the higher energy state. Okay, now the electrons or the atoms which you are taking, the electrons are atoms which are present in the lower energy state. So these atoms or electrons, they want to undergo excitation to higher energy state. But to undergo excitation, they are not having sufficient energy. So this sufficient energy we have to provide. Now that energy we call it as the external source of energy. Now this external source of energy we are using the energy particles which we use, they are called as the photons. Each photon has a particular energy known as E is equal to h nu. Now these particles which are called as photons, they are incident on the lower energy state. Now when these particles, when they are hitting the lower energy state atoms, the atoms become active, which are present in the lower energy state. Now they readily undergo excitation process to higher energy state. So this process we call it as the excitation process, and also as the energy has been absorbed by the atoms in the lower energy state, this process we call it as the absorption process, or you can call it as the stimulated absorption process. Okay, this is the first process which is undergoing in the derivation of Einstein coefficients. Now, next thing is on what factors does this process depends. In order to explain about the various factors on which this process depends, let us assume the energy density, that is the energy which we are calling it as the photon energy. Let us assume it as rho of nu. Rho of nu is called as the energy density. This is the amount of energy which is present per unit volume of the substance. So let us assume it as rho of nu. Then the stimulated absorption process depends on two factors. What are those two factors? First, it depends upon the number of atoms present in the lower energy state. That is, it is proportional to the number of atoms present in the lower energy state. And secondly, it depends upon how much amount of energy is it absorbing from the photons, that is energy density rho of nu. So finally we can say that the absorption process depends on two factors, that is one is N1 and the second one is rho of nu. So N1 rho of nu. So let us remove this proportionality constant and introduce one constant which is represented by B12. Why we are writing it as 12 means the transition is taking place from first level to second level. So that's why we are representing it as B12. So B12 N1 rho of nu. Now what is this B12? B12 is called as Einstein coefficient for stimulated absorption process. B12 is called as Einstein coefficient for absorption process. Okay, now next, second process is stimulated absorption, stimulated emission process. Now we have already discussed this also in the last class, that is a stimulated emission process. Now, what is a stimulated emission process? Now, basically, as we are considering the two-level system, now once we have given the energy, now the atoms are present in the higher energy state. The atoms are present in the higher energy state. Now, the atoms which are present in the higher energy state, they don't want to stay in the higher energy state. They want to get de-excited. That means they want to return back to their lower energy state. Now, in order to return back to the lower energy state, they are having some extra energy. That energy has to be released. But in order to undergo de-excitation, they again require some more energy. So that's why what we are doing is, we are again using the incident particles, that is the photons. And these photons, they are hitting the higher energy state atoms. Initially, they are hitting the lower energy state and they are undergoing excitation. Now, the second process is de-excitation. Even in order to undergo de-excitation also, we have to supply energy which is given by the photons. Now, the photons are incident on the higher energy state atoms. Now, these atoms which are present in the higher energy state, they absorb the energy. Now, they undergo de-excitation process. That is, they are jumping back to their original state. That is the N1 state. This process we call it as stimulated emission process. We are giving energy on the higher energy state. That's why we are calling it as stimulated emission process. And one more point, if you remember, in this process, there will be emission of photons. There will be emission of photons. Here, two photons will be emitted. That is, one by undergo excitation, one amount of energy we are giving, some amount of energy, and to undergo de-excitation, some more amount of energy we are giving. So that's why in this process, two photons are emitted in this process. That's why it is called as stimulated emission process. Now, next, on what factors does this stimulated emission process? Because we wanted to derive the relation. So, in order to derive the relation, what process does the emission also depends? So, firstly, we can say emission depends upon the number of atoms in the higher energy state, that is in the energy state, in the higher energy state with number of atoms as N2. Now, secondly, it also depends upon the energy density, because here in order to undergo de-excitation process, we are giving some energy. So that's why it also depends upon the energy density rho of nu. So we can write this process finally depends on two factors. One factor is N2, that is the number of atoms. Second factor is it depends upon the energy density N rho of nu. Now, remove this proportionality constant. Remove this proportionality constant. Introduce a constant which is called as B21, N2 rho of nu. Now, what is this B21? B21 is called as Einstein coefficient for stimulated absorption. Einstein coefficient for stimulated absorption. Why we are writing it as 2 to 1 means, because the de-excitation is taking place from second energy level to the first energy level. That's why we are using the constant as B21. So, B21 is called as Einstein coefficient for stimulated emission process. Now, the third process is the spontaneous emission process. Now, what is the spontaneous emission process? So, the spontaneous emission process is also similar here, but here we don't use any energy. The atoms by themselves, the atoms on their own, by themselves, once they complete their mean lifetime of 10 power minus 8 seconds, once this lifetime is completed, they automatically on themselves return back to the lower energy state. They also undergo de-excitation process. But here, the amount of energy, the number of photons which are emitted is only one photon. Why? Because it has taken energy, it has jumped to higher energy state, and in the de-excitation process, it is not using any external source of energy. It is just once completing the lifetime, it is returning back to the lower energy state. So there is emission of one photon only. That process we have named it as spontaneous emission process. Now, spontaneous emission depends on what factors? Spontaneous emission depends on a single factor only. That is, it is proportional to N2. You may get it out. Why not energy? Because we are not using any energy. So it does not depend upon any energy factor. It depends only on the number of atoms present in the higher energy state N2. So remove this proportionality constant, introduce a constant which is named as A21N2. A21 is called as Einstein coefficient for spontaneous emission. A21 is called as Einstein coefficient for spontaneous emission process. Now we have got three coefficients. One is Einstein coefficient for stimulated absorption. Second one is Einstein coefficient for spontaneous emission. Third one is Einstein coefficient for stimulated emission. Now to derive the Einstein coefficient relations, let us consider the system is in equilibrium position. The system is in equilibrium position. What do you mean by equilibrium position? How many number of transitions which are taking place to the higher energy state must always be equal to the number of transitions taking place to the downward state. That is, upward transition must be equal to downward transition. That means, what is the upward transition process? That process is first absorption process, stimulated absorption. The stimulated absorption must be equal to sum of stimulated emission plus spontaneous emission process. The absorption should be equal to stimulated emission and spontaneous emission. Now, what is the equation for absorption coefficient? That is N1, B12, N1 rho of nu. I hope you are understanding. So, B12, N1 rho of nu. This is the absorption coefficient. This must be equal to stimulated emission and also spontaneous emission. What is stimulated emission? B21, N2 rho of nu. Next, plus what is the spontaneous emission? A21, N2. Okay, on both the sides you have rho of nu. So for that sake, I am bringing this one this side. So B12 N1 rho of nu minus B21 N2 rho of nu is equal to A21 N2. Okay, now take out rho of nu common from this equation. Then you will get B12 N1 minus B21 N2. This is equal to A21 N2. This is the equation. Now express this equation in terms of energy density. Let us write this equation in terms of energy density. Now the equation for energy density, you will get it as rho of nu is equal to, this is in the numerator part, that is on the other side, A21 N2 by B12 N1 minus B21 N2. You can check the previous equation, that is rho of nu. We have taken it common, B12 N1 minus B21 N2, which is equal to A21 N2. Now I am writing this equation in terms of energy density, that is rho of nu. Rho of nu is equal to A21 N2 by B12 N1 minus B21 N2. Just make some simplifications in this equation. Write some simpler form of equations for this one. Now let us write it as rho of nu is equal to, I wanted to remove this N2. So what I am doing is I am multiplying the numerator and denominator by N2. N2 by N2. Again B12 N1 by N2 minus B21 N2 by N2. Now you can cancel this. Now you are left out with the equation. Rho of nu is equal to A21 B12. Rho of nu is equal to A21 by B12 N1 by N2 minus B21. I again want to convert this also, to remove this term also. So what I am doing is, again I am multiplying and dividing the numerator by B21. If I write the equation in terms of B21, numerator in terms of A21 by B21, so that will be rho of nu is equal to A21 by B21 by B12 by B21. N1 by N2 minus 1. Because B21 by B21, we can cancel it and it will be equal to minus 1. Okay. Now, here, see, in the denominator you are having N1 and N2. Till now, we were calling it as number of atoms in the lower energy state and number of atoms in the higher energy state. Now, let us use one more terminology, which is called as population. Let us use the words N1 and N2 as population. Population in lower energy state is N1. Population in higher energy state is N2. Now, according to one scientist, that is, according to Maxwell Boltzmann, according to this scientist, Maxwell Boltzmann, he has given the ratio of populations from lower energy state to highest energy level system. From lower energy level to highest energy level system, he has given the equation, and the equation for that one is, according to Maxwell Boltzmann distribution, law of velocities, he has given an equation for this population. That population is N1 is equal to Ni exponential of h nu by kt minus h nu by kt. This is the equation for N1. Similarly, you can write for N2. Now, as I'm using only two energy level systems, I will write it as N0. I don't take it as the higher energy state is N1. I'm writing the lower energy state as N0. Now, N2 is equal to, same way equation, exponential of minus h nu by kt. Okay, or this is one way of writing the equation, or you can write it as E, as you know the equation, E is equal to h nu. You can write it as E1 by kt minus, again this also you can write it as E2 by kt. Okay, now in the previous equation you are having the ratio of populations. Now let us write the ratio of populations here itself. You will get N0 and N0 cancel. Now this term goes to numerator. When it goes to numerator, your equation will be N1 by N2 is equal to exponential of, this is in the denominator, it goes to numerator, it becomes plus E2 minus E1 by kt. E2 minus E1 by kt. This is the equation for ratio of populations, that is N1 by N2. Now, as we know that energy of a particle, as we are taking a two energy level system, let us take E2 minus E1 is equal to h nu. We are using a two energy level system. Let us write it as the difference in energy levels, E2 minus E1 is equal to h nu. Now, your equation becomes N1 by N2 is equal to exponential of h nu by kt. This is your equation, which you need to substitute in the energy density equation in place of N1 by N2. Now, I'll write this equation in terms of that, in that equation, substitute in that equation, place this value in that equation. That is, rho of nu is equal to A21 by B21 by B12 by B21 into N1 by N2 you are having. In place of that, I write it as exponential of h nu by kt minus 1. This is the equation which you have got after all the substitutions from the different parts, different things, you have got this one. So, B12 by B21. So, this is the equation for energy density according to Maxwell and Boltzmann. Now, according to some other scientists, as they have given the relation for energy density, according to one scientist, that is Max Planck, Planck's radiation law. According to Max Planck, the energy density which he has given the equation is rho of nu is equal to, according to him, he has given rho of nu is equal to h nu cube by c cube into h nu cube by c cube into 1 by exponential of h nu by kt minus 1. This is the equation according to Max Planck. According to Max Planck, the energy density equation which he has given is rho of nu is equal to 8 pi h nu cube, a small mistake. So that is 8 pi h nu cube by c cube into 1 by e power h nu by kt minus 1. Now take this value, equate these two equations, because these two equations are energy density equations. Now equate these two equations. Once you equate these two equations, you will be getting an expression that, see the denominator and numerator. Now I'll write this equation as A21 by B21 is equal to 8 pi h nu cube by c cube. This is one equation. Second equation is B12 by B21 e power exponential of h nu by kt minus 1 is equal to this equation, that is e power h nu by kt minus 1. So this term we can cancel. You are left with B12 is equal to B21. Now these two equations, B12 is equal to B21, A21 by B21 is equal to 8 pi h nu cube by c cube. These two are called as Einstein equations. These two equations, that is B12 is equal to B21. Everyone, we can generally say that the number of transitions which are taking place, that is how many number of atoms are moving to higher energy state, that many number of transitions, that is that many number of atoms has to also get de-excited to lower energy state. That's why we are getting the equation B12 is equal to B21. Now going to this equation, A21 by B21, that is the Planck's equation which we have written, 8 pi h nu cube by c cube. Now as this is a relation we have got it. Now you can write the ratio of the emission process and the absorption process. Spontaneous emission ratio by stimulated emission. Now what is spontaneous emission? What you got it in case of spontaneous emission, that is A21 N2 by B21 N2 rho of nu. So this is the emission ratio, that is A21 by B21 into rho of nu. This is the amount of energy, rate of emission which is emitted from a system of Einstein coefficients. Okay, this is what is about Einstein coefficients. Now next let us go for the other topic, that is the next topic. What are the main things? What is the basic principle of population of a lasing system? In order to produce a laser output, we require population inversion. Now, what is this population inversion? Population, the word itself is giving you, population is inversed. Now, that is nothing but, you can take a simple way, you can understand in a simple manner. We are having two energy level systems with N1 and N2 number of atoms corresponding to energy E1 and E2. Okay, now in general, in any type of lasing system, in any type of laser system, atoms will be occupying the lower energy state, as how the students like to sit in the last benches. Similarly, here also the atoms want to occupy in the lower energy state. The atoms will occupy in the lower energy state. Now, these atoms, we say for a laser system, always N1 is greater than N2. This is the condition which has to be followed in case of a lasing system, N1 greater than N2. But to produce a laser output, the condition which we require is N2 should be greater than N1. The number of atoms present in the higher energy state should always be greater than the number of atoms in the lower energy state. Now, by some process, by some ways, if you achieve this condition, N2 greater than N1, that particular phenomenon, we call it as population inversion. See, N1. Initially, N1 is greater than N2. By some process, we are making N2 greater than N1. We are inverting the population ratio. So, that particular phenomenon is called as population inversion phenomenon. Okay, in this theory. In general, we say population is more in case of lower energy state. So, by some way, we make the condition N2 greater than N1. That particular process, we are terming it as population inversion. You can see the figures which are there here. The normal population which is present in the lower energy state and the population which is present in the higher energy state, only one atom. Now check the second figure, inverted population. See, in the lower energy state only two atoms are present. In the higher energy state, more number of atoms are present. This process, making this process possible, we call it as population inversion. So, in general, this cannot be satisfied for a two energy level system. Why? Because in a two energy level system, to a maximum, we can achieve N1 is equal to N2. That is, we can make, by some means, we can make N1 number of atoms in the lower energy state is equal to N2 number of atoms in the higher energy state. But we cannot achieve N2 greater than N1. we will not be able to show N2 greater than N1. So for this sake, let us go for a 3 energy level system. Now, in order to explain about a 3 energy level system, let us take the best example for this one, which you will be coming across in the next topics. That is one type of laser which is called as ruby laser. Now, in a ruby laser, it consists of a 3 energy level system. So easily you can understand this concept by using this laser. That's why I'm explaining you by using this concept, ruby laser. So in a ruby laser, as I'm telling you, it consists of 3 energy levels. They are named as, one is named as G state, second one is called as metastable state, middle state, third one is called as higher state. So this is a 3 energy level system. We are unable to explain by using 2 energy level system what is population inversion. So the next energy level we are taking is a 3 energy level system. So for a 3 energy level system, let us take the best example is ruby laser, where we say that the first energy level is called as a ground energy level, second one is called as a middle energy level or metastable state, third one is called as the higher energy level. So in general, what we have come across, lower energy state only the atoms will be present. So lower energy state only the atoms will be present. Now we are supplying energy for these lower energy state atoms by using photons. Now the energy is absorbed by the particles which are present in the lower energy state. Now they jump to higher energy state. Here you can see, please, here we are not using 2 energy level. 2 energy level is second energy state. This is a 3 energy level system. So which is the highest energy level system? H state is the highest energy level system. So after the atoms absorbing the energy, they jump to higher energy state. Okay, this is the first thing. Second thing, in this higher energy state, the atoms will stay for 10 power minus 8 seconds. That means in order to undergo spontaneous emission process, the atoms in the higher energy state will stay for a time of 10 power minus 8 seconds. Once this time is completed, which we have called it as a mean lifetime, once this lifetime is completed, the atoms, they undergo de-excitation to the next energy state. Here the next energy state is the middle energy state, which is also called as the metastable state. The state, middle energy state, is also called as the metastable state. Now, when you see the time in case of these two energy states, now the atoms in the higher energy state, they stay for 10 power minus 8 seconds. Now, if you compare it in terms of time, in the middle energy state, which is called as a metastable state, the atoms will stay for a time of 10 power minus 6 seconds. See the comparison, in which energy state the atoms are staying for more amount of time? In the middle energy state, they are staying for more amount of time when they are compared with the higher energy state. Once this lifetime is also completed, the atoms automatically they get de-excited to lower energy state. Okay, so this is the process what is happening. Now, what is population inversion? So let us take, this is N1 number of atoms, N2 number of atoms, N3 number of atoms. Now I have to show N2 greater than N1. Did you understand the point, concept here? We are taking in the lower energy state, the atoms are present. We have given energy. They have jumped to higher energy state. In the higher energy state, they have to undergo spontaneous emission. So that means they will stay for 10 power minus 8 seconds. Once that time is completed, automatically they get de-excited to the next energy state. As it is a 3 energy level system, the next energy state is the middle state, which is also called as the metastable state. Now, what is a metastable state? A metastable state is a state in which atom or electron will stay for more amount of time when compared with the higher energy state. Now, the best example I gave here, 10 power 8 minus 8 in the higher energy state, 10 power minus 6 in the next energy state, that is the middle energy state. So in the middle energy state, the atom is staying for more amount of time when compared with the higher energy state. That particular state is called as the metastable state. So we can define a metastable state as a state in which atom stays for more amount of time when compared with the higher energy state. Once the lifetime in the metastable state is completed, it undergoes de-excitation to the lower energy state. That means it again returns back to lower state. Okay, now here let us see how population inversion is taking place. Now, as we are saying that in the higher energy state 10 power minus 8, in the middle state 10 power minus 6. Now, to undergo this one here, in this one, when you observe this one, for example, I will take, for example, let us take, there are 10 atoms present in this one. 10 atoms are present in the lower energy state. We have given some energy for the atoms. From this one, 6 atoms have jumped to higher energy state. One by one, they are jumping to higher energy state. Now, from these 6 atoms, 4 atoms, they have completed their mean lifetime of 10 power minus 8 atoms. Now, 4 atoms are getting de-excited to the lower energy state. How many are left here? 2. In this meanwhile, these 2 to undergo de-excitation, these 2 more atoms are jumping here. Now, here how many are coming? 2 are coming. Here how many are coming? 6 has come up. Now, when you see the population, which is more? In the metastable state, population is more. Hence, we can conclude that number of atoms in the higher energy state, N2 is greater than N3. Okay, this is what is taking place. This property or this phenomenon, we call it as population inversion. Okay, so till this population inversion two-level system, today I will close this session. So in the next class, I will be telling you about a 5 energy level system. So with that, we can show how population inversion is taking place very clearly in that topic. Okay, thank you.